In the last lecture, we looked at the impact on common mode rejection ratio by the op-amps and whether we could achieve very high common mode rejection ratios. In this lecture, we're going to look specifically at the performance of op-amps and their common mode rejection ratio and how they impact the overall performance of the instrumentation amplifier. So let's look at the general specification of op-amps. And with all op-amps, the offset voltage, which although in the datasheet is stated as a fixed number, actually varies with the input voltage of the instrumentation amplifier. Here we have a perfect amplifier. We have a 0 volt input signal, and the offset voltage would effectively appear at the non-inverting input. If we then change the input voltage from 0 volts to an input voltage Vin, we would then have appearing at the inverting amplifier input of the amplifier of Vin plus the offset. But that's not the whole story. And in actual fact, what we actually really see at the inverting input of the amplifier is Vin plus VOS, the offset voltage, plus the input voltage divided by the common mode rejection ratio of the op-amp itself. We can actually look at the op-amp and consider it in the same way as we consider instrumentation amplifiers. Both have differential inputs, and in both cases, an input of 1 volt common mode will be equivalent to a differential input of 1 volt divided by the common mode rejection ratio of that op-amp. The difference is that instrumentation amplifiers are used without feedback. They are fixed gain of 100 or 1000 times. And if we look at the equation for a differential amplifier, then we have the output voltage is the differential gain of the instrumentation amplifier times the different signal appearing at the input plus a common mode gain multiplied by the average voltage appearing at the inputs. Op-amps use feedback, so any common mode rejection error must be referred to the input as a change in offset voltage. And also, the differential gain is large and ill-defined. If you look at an op-amp datasheet, you'll discover there's a large tolerance on the open-loop gain of an op-amp. So let's do the analysis of a simple voltage follower. And here we have an op-amp with its inverting input connected to its output. Our output voltage is then the high gain of the amplifier times the difference signal plus a common mode gain times the average signal appearing at the inputs. So if we work through the maths, and I'm not going to do the detail here, we'll end up with an equation that looks like that there. Because the gain is very high, then we can say that this factor here is much less than AV, which is very high, but it's also much higher than 1. So we can now work out a output voltage divided by input, which equals this expression here. And by applying the binomial approximation equals our end figure here. In other words, the error at the output is approximately the common mode voltage divided by the common mode rejection ratio of any given op-amp. And if we look at some typical op-amp common mode rejection ratios, we can see that down here, most of these amplifiers are FET op-amps, whereas the ones with better performance are bipolar op-amps. And these are all plotted against a a log scale of bias current divided by 1 nanoamp. In other words, it's reference to 1 nanoamp. Let's look at the impact of common mode rejection ratio on the performance for our input stage for our instrumentation amplifier. So if we have two independent and independently packaged op-amps, the common mode rejection may or may not track in those two input op-amps. We have no way of knowing. It depends on how they're designed and how they're implemented. If the common mode rejection ratio does not track, which is us taking the worst case, which for good engineering practice is important to do, then the common mode voltage giving rise to a differential output can be up to 2 times the common mode voltage divided by the common mode rejection ratio of one amplifier. So in the worst case, we will assume that we generate equal and opposite outputs at output A and output B, so we will get the maximum worst case scenario. For any given instrumentation amplifier design, the common mode rejection ratio of the overall instrumentation amplifier will always be less or equal to the op-amp common mode rejection ratio. It can never be better than the op-amp common mode rejection ratio. And looking at a table, and these results have been drawn down from a typical distributor that supplies instrumentation amplifiers and op-amps, here we have a few different typical op-amps. And in each case, we're looking at the offset voltage, and we're looking at the common mode rejection ratio. And the very best performing amplifier that I found was an ADA 4528, which had a common mode rejection ratio of 158 dB typical. We've now looked at the impact of op-amps on the practical design of instrumentation amplifiers. We looked at the impact of the resistor values, and we've looked at the impact of op-amp performance, such as common mode rejection. In the next lecture, we'll look at how do we apply some of these to real circuits. Thank you.